Thank you so much for joining. Really always a pleasure to be on these events with Electricity Forum. Thanks a lot, guys. Today, I'm going to speak to an issue that's critical on so many levels, and that is electrical asset reliability and safety. And I put reliability and safety in the same sentence because if you don't have reliability, you cannot have safety. A reliable plant is always a safe plant. Unreliable electric power systems not only cost millions of dollars in downtime and repairs, but they've also got the potential to maim and to kill. So reliability leadership really needs to step up here. They need to focus on the preservation of both physical and human assets. Everybody that comes to work has the right to a safe work environment, and they have a right to return home unharmed. So what this presentation really looks at is the problem, which is an unreliable aging infrastructure, and specifically around electrical assets, whether it be substations, transmission, distribution lines. We all know, we see it in the news, we hear it every day, that the infrastructure is aging and it's not able to keep up with the demand. What I'm going to present is a solution, the technologies that can give us an early detection. Early detection is everything. We need to know when problems are about to occur so that we can get on it, schedule repairs, order parts, and know before an outage event shuts us down. At SCT, we have a simple mission. We wake up every day with one thing in mind, and that's to enable our customers to achieve their operational objectives by advancing the reliability of their assets. And we do that by providing leading edge technologies built around ultrasound, the ability to detect ultrasound, high frequency sound, convert it into audible sound so that we can hear and know when our assets are changing in their operational condition. Today, two topics to cover. One, what is ultrasound? And two, electrical maintenance. We'll start with what is ultrasound. And in this, we're going to talk about sound characteristics, friction impacting and turbulence, and the 8 application pillars. So really what this is just let's call it an ultrasound 101, just a real 30,000 foot level on what is ultrasound and how can it help make my life better in context of reliable electric assets. And then once we've covered that little briefing, we're going to jump into electrical maintenance. And with electrical maintenance, we're going to talk about these topics, the importance of electrical maintenance. I'm going to take a quick look at NFPA 70B and NFPA 70E, 2 standards by the National Fire Protection Agency, so we can have a look at what each of those standards, what their purpose is, what they mean to us, and how they can help us find common failure modes. Then we're going to look at a couple of case studies, and we'll finish things by looking at specific ultrasound technologies that we manufacture and provide globally for our customers to maintain their electrical assets. So let's just jump in to what is ultrasound. And I always like to start this segment by talking about what is ultrasound in terms of the 3 different, sorry, I gotta adjust my screen here because I can't see one thing. There we go. Sorry about that. So in terms of sound characteristics, what we want to look at is the 3 different classifications of sound. The first one being infrasound. Infrasound is low frequency, below the human range of hearing. Certainly good for seismic sensors to detect earthquakes and tsunamis and things like that, underground detonations, but not really much good for humans because we can't hear them. Audible sound, so in that 16, that's not right, 16 to 20 kilohertz, no, it's basically up to 20 kilohertz and just a few hertz. So I think it's supposed to be 16 hertz to 20,000 hertz is the range or the scientific definition of human hearing. I can attest on my latest hearing test that I can only hear to about 11 or 12 kilohertz, but that's partly due to injuries, in my youth, and being exposed to high noises through my working career, and just the fact that I'm turning into an old guy. Uh, so what we tend to lose as we get older is our higher range, our higher frequency ranges. And the good news for us is that the human sounds, our voices, and most of the sounds that we listen to are in that sweet spot of around 2 to 5 kilohertz. So I'm going to put off getting a hearing aid for a little bit longer yet. When we get above 20 kilohertz, we are now in the range of what we call ultrasound. And from 20 kilohertz on up to infinity into the millions of hertz, the megahertz, we're now talking about things that we cannot hear. The one thing you'll notice as I work through these slides is that the wavelength of the signal, that signal got longer in the lower frequencies and then shorter in the higher frequencies. And what that means to us is that as we go higher in the, how do we get rid of this? Exit. As we go higher in the frequency range, that wavelength becomes shorter and shorter. Well, the shortening of that wavelength produces three characteristics of ultrasound, which makes it very useful for us as as condition monitoring technicians, as people looking to find different problems with assets. The first of those characteristics is distance. I hope those lines aren't going to stay on here the whole time. Here. Well, we'll just put up with them. So the first thing is distance. The lower we go in the frequency range, the longer the distance that sound will travel through the medium, whether that medium's the earth or the air or through steel or whatnot. As we get into the audible range, the distance that sound will travel before it's attenuated and absorbed is significantly shorter. And when we get into the ultrasonic range, the distance becomes even shorter yet. And so these characteristics are something that are very useful for us, because when we're trying to find the source of an ultrasonic signal, we don't want to be interfered with by competing signals from other assets. So if I'm focusing on a particular spot of a substation, I want to focus just on that spot, and I don't want to hear ultrasound from other competing areas. I'm just going to restart this because those. There we go. Well, they're still there. The second characteristic of sound is directionality. So when we listen for infrasound, the directionality is 360 degrees. The sound is traveling in every direction. As we get into audible sound, this is not a Pac-Man. It's to display that if the sound source is here, that the signal becomes more narrow and more focused. If you're ever walking behind a person and that person in front of you is speaking to you, but they don't turn and face you, you have a more difficult time hearing them, because the sound that they produce doesn't want to go backwards, it wants to go forwards. It doesn't want to go backwards to where your ears are. Well, as we go higher and higher in the frequencies, that directionality becomes even more so. So when we get into the ultrasonic frequencies, we start to see that if we look at this little pie shape here, that's the path, or that's the direction that ultrasound is going to travel through the medium. That directionality makes it very good for us to use ultrasound to pinpoint the exact source or the exact location of the signal. The third aspect of ultrasound propagation is boundary behaviors. So ultrasound, unlike the bass sound from a subwoofer, for example, doesn't want to stay inside. You know, a subwoofer in the trunk of a car is going to boom, boom, boom. It's going to It's going to pass through steel and pass through windows, and we're even going to feel it before we hear it. But ultrasound that's produced inside of a body, say inside of a transformer, for example, or inside of a switchgear panel or an electrical cabinet, that ultrasonic signal is going to stay inside that containment until we put a contact probe or some kind of an ultrasound sensor or a waveguide to draw the signal out and into our instrument. So again, that's a very good characteristic for us when we're trying to locate exactly where a signal is coming from, as you'll see in one of the case studies. We like to say that ultrasound owns the apex of the P to F curve. And I'm just going to let this diagram run now. So the P to F curve is designed for us to understand from the point of D, design, to I, installation, to P, potential failure, to F, functional failure, when an asset is degrading to the point of that functional failure. And as condition monitoring technicians, our job is to keep this line as straight and flat for as long as possible. And to do so, we use technologies like ultrasound, like vibration analysis, audible noise, heat thermography, oil analysis, lots of different condition monitoring technologies to help us understand when our assets need to be maintained. Ultrasound sits here, just past the potential failure. So in other words, as soon as a new asset is commissioned and starts doing its job, ultrasound plays the earliest role, or gives us the earliest indication that the condition of that asset has changed. So we can rely on ultrasound to be our first line of defense against asset failure. We like to say that ultrasound gives us asset fitness, and we emphasize the word fit as part of the word fitness because the three symptoms that we can detect, or the three sources of ultrasound, come from friction, rubbing of components together, impacting, when components are banging against each other, and turbulent flow, such as leakage or partial discharge, where the air molecules are disrupted in creating this turbulence. Well, all three of those, friction, impacting, and turbulence, produce ultrasound and are therefore, ultrasound is a good fit to help us find those exact symptoms and know when things are going to fail. From that, we've discovered that there's 8 application pillars for ultrasound, and those are on the screen there: mechanical, leaks, lubrication; electrical, which we're talking about today; valve inspections, steam trap inspections; hydraulics, and tightness testing. I'm not going to spend time going into all of those, other than to say that each one of those produces either friction, impacting, turbulence, or a combination of all three. Especially with electrical systems, we're looking at turbulence, which is produced by partial discharge. If I reorganize those and I look on the left at leaks, valves, steam, and tightness, I can learn how ultrasound can help me eliminate waste. And by eliminating waste, I also can help my company achieve its sustainability initiatives and just help make the planet a better place. If I shuffle them again, and I put lubrication, valves, steam, electrical, and hydraulics and mechanical as my priorities, now I have the power to eliminate unplanned downtime from all 6 of these. And when I can eliminate unplanned downtime, that means that all my downtime is planned. And when my downtime is planned, it enables me to work safely. When I work safely, I eliminate workplace accidents. So ultrasound helps me contribute to a better environment and a better planet. It helps me plan our downtime, so that helps us be more economically viable. And most importantly, ultrasound helps us to have a safe workplace. So that's your ultrasound 101. That's the 30,000 foot view. If you ever take a category ISO Cat 1 training from us, that those few slides takes more like a half of a day to cover through. But those were the highlights. Those are the things you really need to know just to connect the dots on the rest of this presentation. The importance of reliable power systems. Well, we can put that in a lot of different contexts. Reliable power systems help keep the lights on. They help keep motors turning. If you're in a hospital in the ICU, they help keep the medicine dripping. If you're working in an institutional building or commercial building, they help keep the air conditioning running. When we don't have reliable power systems, we have darkness. When we have darkness, it really emphasizes these four darn lines that I can't seem to get off of my screen. I'll figure it out probably when I get off this call. But they're there for the duration, so let's just live with it. So that is, my friends, the importance of reliable power systems, is making sure we can keep the lights on and keep everybody happy, safe, warm, and comfortable, and keep our manufacturing plants making things. Electrical failures often start small and then they go unnoticed until it's too late. And again, that plays right into the sweet spot of ultrasound, because ultrasound detects microscopic, or I like to say microsonic signals, which only tell us that things are starting to go bad, but we still have a big window to make them better. Unreliable assets are dangerous and inefficient, and they add stress to our already aging infrastructure. Let's talk a little bit about the National Fire Protection Agency's mandates to help protect people and to protect assets. These are electrical safety standards which focus on reducing risk. The first one is known as NFPA 70E, and the E on the end denotes that this is a standard that was written to protect people from electrical hazards. This is essentially the electrical safety code that your electrician follows when he comes to do work in your plant or in your home. And they establish safe work practices to prevent shock, arc flash, and arc blast. They define approach and arc flash boundaries. They require hazard identification, risk assessment, and control measures. They specify what personal protective equipment we need to choose, how we work our lockouts and our tagouts, and what training people who are working on or around electrical assets must undergo. All of the NFPA 70E aligns with the OSHA electrical safety requirements. NFPA 70B, on the other hand, is a guide for maintaining equipment for reliability and safety. So this is playing into the hands of condition monitoring technicians. This is what's helping us as those technicians, as those reliability engineers, to maintain our equipment. And in the most recent edition of NFPA 70B, there has been some dramatic language adjustments, which if you're responsible from a management point of view on electrical assets, you really need to know about these. NFPA 70B defines electrical maintenance programs for assets. It promotes preventative and predictive maintenance practices. And I'm going to say that the word promote is now been upgraded to mandates, because preventative and predictive maintenance practices are now required. It's the documentation that those practices are in place are now a requirement of all the inspections and tests that you do, whether you're doing in-house infrared thermography or outsourcing it, or ultrasonic scans or any other types of tests. These are mandated tests, but you also need to, in the event of an inspection or an audit, prove through documentation that you're doing these. NFPA 70B serves as a complement to NFPA 70E by ensuring equipment is in a safe operating condition always. And I won't, this is just a summary slide, and I think these slides will be available to anybody who wants them. But basically, this table just gives us a comparison between the full title, the primary focus, the objective, the key theme, and the target audience for both 70E and 70B. So let's not spend more time on that. So let's jump into understanding what partial discharge is. First of all, in simple terms, it's the most common early failure mode for electrical systems. It's a localized electrical discharge that occurs within insulation systems, but it's a discharge that does not completely bridge the electrodes. In other words, it can be caused by dirt, by corrosion, by a gap. And it means that the dielectric material or the insulation hasn't yet failed, but it is in a deteriorating, degrading state. For ultrasound inspectors, partial discharge is the first audible clue. It's actually an inaudible clue that an electrical asset is under distress. We write audible in the slide because ultrasound has that superpower of taking the inaudible and making it audible, thus giving us superhuman hearing. Ultrasound provides early detection and helps us prevent full-on insulation failure, which can result in a more catastrophic event, whether it be a fire, a transformer fire, an explosion, or an arc flash or an arc blast event, which we obviously want to avoid. So what are some of the causes of partial discharge? Well, partial discharge occurs when the electric field strength exceeds the insulation's ability to resist ionization. The causes include voids, cracks, contamination, sharp edges. They're caused by poor workmanship typically, but also by moisture, corrosion, and aging. The one critical thing that we all have to remember or all need to know is that partial discharge, once it starts, it begins to accelerate its own damage. So partial discharge in itself doesn't manifest itself out of thin air. It happens because the dielectric material is beginning to break down. But once that partial discharge is there, the ionization of the air molecules around the partial discharge field produces gases which are, let's say, corrosive, let's say not friendly. So they start to accelerate the damage to the insulating material. Well, the answer to this question is all over. The partial discharge is present in most medium and high voltage systems. Anywhere where insulation might be aging or where it's stressed. Switchgear, so we're going to have internal corona and tracking and eventually arcing inside of electrical cabinets, motor circuit control panels, those types of things. In a lot of the cases, partial discharge is enclosed in a cabinet, so it's not obvious for infrared thermography. If the partial discharge does in fact generate heat, which most often it does not, even if there is a direct line of sight, which is what infrared thermography needs, there's not always going to be heat. But when partial discharge is enclosed inside of a cabinet, well, it's ideal for non-intrusive ultrasound inspection. Another place where partial discharge hides is inside cables and joints, especially if you have cables that are bending. We try to keep our cables, especially our medium and high voltage cables, as straight as possible and as short a lengths as possible. So any bends in the cables compromises the material structure of the insulation, and that's where partial discharge begins. Transformers and bushings, line bushings, connections on phases, the internal voids there can allow for partial discharge as well. And then VTs and CTs, surge arresters, capacitor banks, lightning rods, those types of things. Ionization. is what is produced when you have partial discharge. It forms ozone and nitrous oxide, which combines with moisture to produce nitric acid. And if you look here around these cables and around the outside of this, anywhere where the cables are touching or where the cables are touching an insulating material, or in this case, just the channel, you have that white powder right where my mouse is, and that white powder is a visual sign that there's some partial discharge activity going on there, which is going to further lead to corrosion and insulation deterioration. Looking at that same image with an infrared with a thermography camera, well, it may not produce detectable heat, and this one definitely did not. As you can see, it's just cool colors around that internal corona discharge. But it eventually is going to lead to flashover and fires. Then you'll have heat, but then you don't have a window to detect it. So these types of problems are detected early with ultrasound. We can run routine inspections and routine maintenance and plan to have these assets either repaired or replaced. Again, that white powder that we see at the site of a corona, if you look at these medium voltage cables, again, where the yellow circle is, we can see the white powder. And again, we don't want to have these cables touching each other. The ionization of that air around edge-energized conductors typically only occurs above 1 kilovolt. Typically, we will not produce enough heat to be detected with an infrared camera. But when we detect them with ultrasound and we look at that ultrasonic signal, because we can record it, when we look at that ultrasonic signal in either the spectrum, the FFT, or the time waveform, we see consistent amplitudes and repeating patterns. And depending on where we are in the world, we'll also see 50 or 60 hertz harmonics, which are indicative of the line frequency. So, and here's a good example of the time waveform. And here's what it sounds like. Just a classic buzzing signal. But when we take this time waveform, this is 2 seconds. This is basically, this whole time waveform view here is just 1 second, 1 second of data. So we've really expanded it out, and each one of these bursts is correlating to the line frequency of that electricity. So that's corona. Tracking is a whole other kettle of fish. It's another term. It's a term that we use to encompass surface discharge across contaminated insulation. And so if you look, this middle picture is really the best one. You see all of this branching out, and this is surface discharge, and it's forming a path through the material to ground. It's trying to find a path to ground. You get this crackling, sizzling sound if you're using an ultrasound detector to find it. In the, you won't see a whole lot in the FFT, because FFTs, or spectral analysis, is really designed for repetitive events, and tracking tends not to be repetitive. It tends to have intermittent bursts. In the time waveform, also bursty and uneven amplitudes. And tracking can occur at any voltage. So this is what I mean. Here's the time waveform. I'll play the sound for you in a second, but what you see is, you see bursts, and then it's quiet for a little bit, and then more bursts of energy. And this is typical of tracking as it's making its way through the insulating material. So here's a real live look at a bus bar inside of a switchgear cabinet. And what we can see here is, we'll just draw your attention to the actual carbonized path of the discharge, this branching this way and branching this way along the surface of the bus bar. If you look up here, you can see dust, you can see dirt, and we just move the mouse over to there, we see that faint purple glow, and that's indicating active arcing. surface discharge. You might not be able to see that with your eye because it's behind a cabinet. We've opened the cabinet after we safely opened the cabinet after we detected it. You also might not see any heat from that unless you have a direct line of sight to it. When you have dust and debris, you have increased surface conductivity over time. And so here we can see that an example of an external surface discharge progressing towards arcing if this isn't detected in time. I would say that this was not detected in time, but it really is, it's relative. It's contextual. I mean, the asset's still functioning, so we don't have an outage, but it's deteriorating. I don't think that this can be fixed. It needs to be repaired. That means we have a longer repair time. That is more than just blasting some dry ice or something in there to a little dusting and cleaning. This isn't simple maintenance anymore. This is going to require a planned shutdown. So it would have been nice to detect this sooner than where we're at now. This is a time lapse of the formation of surface tracking. So let's just start playing it now. And don't ask me, I don't know how long this experiment ran. This is a lab experiment, but you can see that this is the process of surface tracking generating and slowly gnawing its way through the insulation material. And then when those two connections join up, electricity finally gets what it's thirsting for, and that is to find its path to ground. That's all it's trying to do, is find a path to ground. Here again, we're inside of a glass tube, and we've obviously sped things up, but we can see that once that partial discharge starts, there's no stopping it, and it just continues to evolve and continues to eat itself from the inside out. Here is some partial discharge that we detected inside of this high voltage cable. And you can see the damage that was done because it was not detected in time. It turned into a cable failure and a fire. The third progression of partial discharge is arcing. So we started with corona, which is really just nuisance sometimes. We've progressed to tracking. Now we're at the stage of arcing, where we have high energy discharge bridging the conductors. Remember, early partial discharge, the discharge does not bridge the gap between conductors, but with arcing, it actually bridges the conductors or finds a path to ground. Again, you're not going to see anything in the FFT or in the spectrum. It's broadband, it's chaotic, it's not sinusoidal. In a time waveform, we're going to see exactly what we see here: sharp, audible, violent bursts. In the ultrasonic condition indicators, we're going to have a high crest factor. So that's looking at the impacting or the high spikes of voltage like we have here and over here, versus the overall noise, the RMS of this whole signal. And this is an immediate safety and reliability risk. If this is going on inside of a closed cabinet, there's a good chance that there's a buildup of combustible gases. And when you open that cabinet, you're going to have an inrush of air. That air is going to mix with the gases and the arcing, and you're going to have yourself a quick trip to the sun, because an arc blast has temperatures on par with those at the surface of the sun. So we don't ever want to be in that situation. Even if you've got the best PPE in the world, you have a high risk of not walking away from an arc flash or an arc blast. Ultrasonically, that's what you're going to hear. And when you hear that, it's time to call somebody. It's time to shut things down. Electrical inspection with ultrasound, the best practices. So infrared and ultrasound, you want to use ultrasound in between your annual infrared scans. Or if you're going to do an infrared scan and you want to open up a panel or you want to open up a cabinet, then do an ultrasound scan around the cabinet prior to opening it up for the infrared inspector, So you have a higher level of confidence that that there's nothing going on inside there that could create an arc flash or an arc blast. And of course, you got to be suited up. If you only use infrared, you may miss conditions that infrared cannot see, or you may miss conditions that don't produce heat. Our recommendation is to use infrared and ultrasound as complementary technologies. One sees what the other one can't hear, and one hears what the other one can't see. And then finally, to analyze the sound files in the frequency and the time wave in order to diagnose exactly what the problem is. So this transitions us from Ultrasound 101 to electrical maintenance to the SDT product of ultrasonic on ultrasonic solutions. And we have a host of them here. Most of these can be quite useful for inspecting electrical. The SDT 200, the 270, and the 340 are all great handheld devices to carry around for switchgear inspections, for connecting parabolic dishes or long-range sensors so that we can hear problems from the safe side of the fence. Here we have what we call the SonaView, which is an acoustic imaging camera. This camera has 112 digital ultrasound sensors, as well as a long-range, high precision camera. So with the SonaView, we can take a picture of an electrical asset, and if there's any kind of partial discharge tracking or arcing going on, you'll see right here where my mouse is encircling, you'll see a little burst. And that little light burst says that that's where there's a source of ultrasound. That part of the asset needs to be inspected. So this is a great little camera for walking transmission and distribution lines, for listening for corona discharge, or standing on the safe side of the fence and taking a visual, either images or video of a substation or any assets where you can't get close. The Vigilant is a permanent system. We've sold quite a few of these in Asia Pacific, specifically in Indonesia, but also in Thailand. And what we're doing with these is we're putting airborne ultrasound sensors inside cabinets, inside electrical cabinets, and then we're cabling them back to the Vigilant. And the Vigilant is doing a 24/7, 365 analysis, or let's say just a monitoring of those cabinets to be sure that there's no changes in their condition. We've also connected contact sensors to the outsides of oil-filled transformers. And so with the Vigilant, we can put up to 8 sensors onto a transformer. So we can have airborne sensors pointing at the phases. We can have contact sensors listening for partial discharge inside of the oil. And this becomes a total 24/7 system for monitoring transformers. A couple of different contact sensors. So this sensor here in the middle, the RS2T, this sensor here with a threaded mount or either a magnetic mount gets stuck directly onto either a switchgear panel so that we can hear through it, or it gets permanently mounted on a transformer if we're doing any kind of long-term condition monitoring on that transformer. Our airborne sensors, so the flexible sensor here in the bottom left, that's very useful for scanning around the seams, any air gaps in MCC panels, in electrical cabinets. It allows us to hear what's going on inside of them. And then this up here in the top right-hand corner, the Paradish 2. The Paradish 2 is very useful for long-distance inspections of transformer and transformers, and as well as transmission and distribution lines. Give you an example of that. Here on the right, we have our junior technician. Not a lot of experience or skill required here, but he's got himself some headphones connected to an SDT 340 ultrasound detector and a parabolic dish. And this parabolic dish has a laser dot on it. So we can scan around the phases of this transformer and figure out if there's any potential hotspots. So that's easily documented. You take a picture and you say, we know exactly where the problem is now, and that gets into a work order for future maintenance. Look at a couple of case studies. So we have one here. So an electrical inspection. This is a high voltage transformer, and we inspected it with ultrasound. We used the SDT 340. To refresh your memory, that was this guy right here on the right that gives us the time waveform view right on the screen. And so using the 340 with the flexible wand attachment, and again, the flexible wand was this fellow right here. And the signal that we heard through the air gaps of this this ventilation at the bottom, well, we took those into the FFT, and lo and behold, here we can see the 1, 2, 3, 4. We can see all of these harmonics, and these harmonics are all lining up with 50, 100. Oops, lost my picture. These are lining up with the 50 hertz. You can see them over here. So number one is at 100 hertz. 2 is at 200 hertz. 3 was at 300 hertz. These are all harmonics of the line frequency of this system, which is obviously running at 50 hertz. And I just said that. The recommendation was to perform a cleaning on that part of the transformer to see if the amplitude of those harmonics decreased, or better yet, if they disappeared altogether, which is what we want. Another typical inspection here is a commercial three-phase pad-mounted transformer. And using a contact probe on the outside of the transformer, we were able to pick up the sound of ultrasound, the sound of electrical problems. So we had somebody qualified to open up the panel for us. Once the doors were open up, we were from a safe distance with the parabolic dish. We looked at the left insulator, the middle insulator, and the right insulator, and this is what we heard. So the left insulator is pretty quiet. We can hear that it's quiet. We can also see in the this in this time waveform that there's very little activity there. So if we move over to the middle insulator, you can see that there's a lot more activity picking up here, and that the sound has become the amplitude's grown. And if that, just for a second, I'll take you back to the early slides here when I talked about distance, right? Distance and attenuation of signal through the air. So in the ultrasonic range, as we go higher in the frequency range, that attenuation happens. And this is why when I'm pointing, also the directionality of the signal, if I'm pointing at this phase, I'm not going to hear what's going on in this phase, because ultrasound is much more directional than audible sound. If I move over to the right insulator, I can now see that the amplitude of my signal has dramatically increased. And just to go back and look at the scale here, the scale of the y-axis is 1,000 microvolts. And it's also 1,000 microvolts here and 1,000 microvolts here. So we've intentionally scaled all three of these time waveform views with the same y-axis, so that they're, it's comparative across. And we know with no uncertainty, zero uncertainty, that the problem is coming from this third phase. And now, again, this could be very early in the failure curve. And if it's early in the failure curve, it could be simple maintenance. It could be some dry ice cleaning. That's all we need to remediate this and get it back to working. When I take that signal from the time waveform and I put it into the spectrum, I just happen to have it at in CPM instead of hertz. So if I want to take that, like if I look at the first signal here, it's 3,600. If I divide that by 60, 36 divided by 60 is 60. 3,600 divided by 60 seconds is 60 hertz. So that's, I know that this is, that each one of these harmonics is part of the line frequency of the voltage. So I know that this is only partial discharge. It hasn't advanced to tracking yet. It hasn't advanced to arcing. So I know that I'm very early in the failure curve, and that simple maintenance is something that's going to probably cure this problem. Yeah, and that's the text is what I just said. So I'll just push on. 2000 kVA transformer. Again, inspecting through these vents using an SDT340 and a flexible wand. An absolutely horrible sound. The only thing I could think of worse would be running my fingers down a chalkboard. Just to correlate, we also took an infrared thermography image of this same transformer using our FLIR camera, and we can see clear hotspots. We know where the problems are. So again, this is a case where we can use both ultrasound and infrared thermography as complementary technologies. Just a quick word on the SDT340 then. It's a multifunction data collector that has the ability to have sensors plugged in to make it airborne ultrasound, contact or structure-borne ultrasound. In addition to that, we can plug in a vibration accelerometer. This gives us the ability to listen to and take data off of rotating equipment, such as cooling fan motors and other, water cooling pumps and those types of things. We can collect temperature measurement, and it also has a tachometer built into it. It has an internal database, and it reports to software, which allows us to do measuring, trending, and analysis. So all of those earlier images that I showed you of time waveforms and spectrums were all collected with the 340 and then analyzed in its software. And this can be applicable to transmission and distribution lines, substations, switchgear, motor circuit controllers, transformers, and much, much more. Because we can look at the time waveform here and the FFT on the screen, it's actually not a bad little tool for doing an on-screen and in-field analysis. And again, it's compatible with the UAS3 software, which here's a simple screenshot. And if I wanted to build an asset tree on the left of all of my electrical assets and all the measurement points on my electrical assets, say, for example, I have a switchgear room full of electrical cabinets, and each one of those cabinets has a unique identifier. I could build an asset tree and name each of those unique cabinet panel numbers. And then I could just send somebody out, and it doesn't need to be a Cat3 vibe person. It could just be a junior technician can go out, put his sensor on each of the panels, and then collect both a time waveform, an FFT, and a static trend data. And I can start to build a measurement database, or let's say a condition monitoring database of all of my electrical assets. And what does this do for me? Well, it allows me to build that centralized database where I can organize my inspection routes and create a recorded asset history. I can have different dashboards that I can make for my own purposes, and I can do the advanced analysis with a time waveform in the spectrum. But what's not mentioned on this slide, and maybe the most overarching point, takes us back to NFPA 70B. If for some reason I have an audit or an inspector come in and audit my facility and say, show me that you're following NFPA 70B, I need to see a documented proof that you're doing all of the right things. I just need to open up my computer and show them this database, and I can pull some reports out. And just like that, I can say, yes, sir, I am following this to a T, and I am in compliance. Okay, Sonoview acoustic imaging cameras. Again, 112 did 112 digital MEMS sensors, which are on the opposite side of this camera, and they're arranged in a precise configuration to deliver high sensitive detection and distance. So we have a very narrow range of focus, but we can detect problems up to 150, even 200 meters away. And I love that because that keeps me, again, on the safe side of the fence, especially when it comes to substation inspections. There are onboard diagnostic features. So in addition to capturing an image that clearly shows me where electrical activity is happening or a video, I can also look at the PRPD graph. PRPD, if you don't know, stands for phase resolved partial discharge. And that phase resolved partial discharge looks at different phases of the complete cycle of a signal. And I can use that to determine whether or not, or what type of electrical fault I've just discovered. This Sonoview also has GIS integration. So if I'm out doing transmission and distribution line patrols, and I log a defect, I can later go back into my report and use my GIS integration to know exactly where I was, and I can map where all of my defects are. Nice feature. So here's a typical image, all right? On the top, I've got just a basic, looks like a polyceramic insulator on the middle line of this medium voltage residential line, but I can see from that color burst that I have a partial discharge activity. And my PRPD graph is here. And I can see from that PRPD graph what type of defect that is. And this PRPD looks completely different from the PRPD graph on this transformer. And again, also this image doesn't really show that well, but it was cut off on the bottom a bit. But again, another line insulation issue here. So let's take a look at the three potential fault patterns that we can detect with the AI in the Sonoview Plus. First of all, when I have just a single burst like this is the full phase. The single burst here tells me it's corona partial discharge. When I have a double burst, it's surface partial discharge. And when I have a more of a pattern like this, it's floating partial discharge. And so the difference between surface partial discharge and floating partial discharge, this is just another language for corona, tracking, and arcing. So we recommend at SDT to have a multimodal strategy. We want you, obviously, this presentation emphasized the strengths of ultrasound. This is by no way or means me saying use ultrasound and ultrasound only. A full and effective condition monitoring program for medium and high voltage electrical assets combines infrared thermography, transient earth voltage, digested gas analysis for full coverage. We want all four of those technologies used. Each of those methods is supported inside of the NFPA 70E for safety and 70B for condition monitoring and maintenance. We want you to use ultrasound first as your first line of defense to screen. You use the others for confirmation, but the screening that something exists, something hidden exists, produces a level of safety for you. When we have correlated data from 4 different technologies, we have better prioritization for planning the maintenance, and we get a quicker ROI on our NFPA 70B maintenance and condition monitoring strategy. When we can have evidence converging from multiple technologies, we can make more confident decisions. And when we can make more confident decisions, ultimately we lead to a more safer facility. And again, I'm going to end this out with this slide here, which shows us just a table. So down the left side, we have the asset type or the asset fault. So switchgear, internal partial discharge, overhead lines and bushings, transformers, cables and terminations, and resistive joints and loose bolts. So we can see based on the technology that you use, whether it's ultrasound, infrared, ultraviolet, TEV or transverse voltage and radio frequencies, and DGA. So we can see where each of those technologies excels. Ultrasound has 4 check marks out of 5. The others have fewer. I think the biggest check mark here goes for early detection. And early detection for me means, and I know I'm repeating myself, but what early detection means for me is knowing that I've got an earlier window to plan my maintenance strategy. I've got an earlier window of detection means that I'm not having collateral damage, because remember, when you have partial discharge, what happens is it starts to accelerate the decay. So the sooner I detect it, the earlier I can prevent things from spiraling out of control. That pretty much wraps up. I mean, I've run out of slides. I can talk forever, but I don't have any slides left. So I think I'm going to stop it at this point and turn it back to see if there were any questions that this may have raised.